Hey, sorry. As you guys pop in, we'll probably give you guys 3 or 4 minutes. While you guys pop in, I'm gonna go turn my dryer off. So hang tight. You can check out the chat box. Sorry about that. Welcome, welcome. We're going to give people till about 2:15. Probably not that long. We'll wait till there's about 6 or 8 people. While you're stopping in, if you have any questions, you can go ahead and drop those in the chat box. Don't forget that chat box will stay with us online. And if you need to pop out or pop back in, you can just look at things right on YouTube. I am working on getting the questions into our YouTube so that we can look at those. I know, high tech around here. How is everyone? If you're just hanging out, I'm so glad you're here. Sorry about the tech delay. If you would like, you can go ahead and drop your favorite emoji in the chat. Say good afternoon. This is my home office. So Clarissa asks, do you have a set number of questions for the exam? No. I am not saying it's not done yet, but I haven't finished writing it yet. So what we will see next week's probably not the right expression. What we will see later this week is that it'll be similarly formatted to all of the others. Hi, McMoogie. Yes, I do we have one titration problem in the deck already. Hold on. Trying to get all of the questions in a chat box so that, yes, when I share my screen and read on my iPad, what other questions do you guys have as we get ready? Jive turkey is correct. There is an example problem. Brielle asks, what is the best study tool? In my opinion, I would use, I would look back over any and all problem sheets, whether they come from the in-class or the in-class assignments, the at-home assignments, I won't say all the assignments, but any of those will work. Hold please, there's 2 more questions that I need to pop into a text box so they will live stream in a fantastic way. maybe not, obviously. It's been a while since I've gotten to live stream from my house. This is how I taught during the pandemic. So, all right, the rest of those. One last. I'll just take this copy. Okie doke. So, Brielle asks about study tips. That's not what I'd like that to do. I would work example problems. You can look back at Alex. You can redo any of the assignments that we've done in class. You can poke around on my YouTube channel and find old examples. Some of them will be in the same format. What we will see shortly is that the question will go right here, I think. If I've done this correctly, we'll have a question right here, and then you could pause the video, and then you could go ahead and look at that, if that spoke to you. It might be that my live stream was a little late. We had some minor technical difficulties. It required a few restarts, and like everyone, I waited till the last minute to make sure everything technologically worked. My guess is it was just late because we started at about 2:09. So let me move one thing so that we don't hear it all fall on the floor in just a second. Nope, I need to add that. Perfect. All right, so number 1. It's not exactly perfect, but hopefully you can read this question. It is the same question, just some text in case you didn't see the worksheet. This question right there, you can find online on the final exam review questions. If you have other questions, so I know someone else asked for a titration. This is one. We can do, or we can think about other ways that you have titrations, and we'll talk about how this one might be different from what you see on the exam. So in this question, it says, a chemistry student wants to standardize a fresh solution of sodium hydroxide. He weighs out 1.28 grams of oxalic acid, gives us the formula, and it says it's diprotic. Diprotic means that 2 hydrogens are going to come off. And from there, he's going to dissolve that in 225 mils of distilled water. The student then titrates the oxalic acid solution with his unknown sodium hydroxide solution. When the titration reaches the equivalence point means that the moles of acid and the moles of base units are the same. The student finds that he used 17.3 mils of sodium hydroxide solution. What is the concentration of the sodium hydroxide solution? So, number 1, we need a balanced chemical equation. And so, luckily, this problem gave us the H2C2O4. So, we are going to make try to get that a little bit closer. That's close. So we have H2C2O4 plus NaOH. Now, this question was adapted from Alex. So if I did, I would tell you what oxalate is. Although that is one of your common ions, so you should know that oxalate is C2O4 2-. So we are going to lose these 2 protons, and they're going to interact with the OH. And then we're going to have sodiums. So we have Na plus C2O4. Now, C2O4 is 2-, so this is sodium 2, or there are 2 sodiums. And then we're going to add 2 H2O as the other components. So now we have let me erase some of this exciting stuff I drew all over that. So now we have a balanced chemical equation. Don't forget, there's a list of strong acids and strong bases in the chapter 4 notes. You need to know those. If I pick something else, anything special, I will, to be quite honest, just give it to you. But likely you're going to have to come up with a balanced chemical equation. So from here, we know the relationship. Sorry, I forgot to balance that out. I was very excited. So it's 2 NaOH to give you the 2 sodiums, and the H2 here, and these 2 OHs make H2O. So now we have a balanced chemical equation. From here, we know in the titration, the moles of acid are related to the moles of base. So we need to figure out the moles of acid. In this problem, it gives us a weight. So we're going to take our 1.28 grams of H2C2O4, and then we're going to divide that by the molar mass of 90.04 in 1 mole. And this gives me 0.01422 moles of H2C2O4. Now we need the ability to turn this into sodium hydroxide. We can do that using the stoichiometric coefficients. Stoichiometric coefficients are the big numbers in the equation. So for every 1 mole of H2C2O4, there are 2 moles of NaOH. Now this, when you plug this into your calculator, I got 0.02844 moles of NaOH, which is good, but it asks for the molarity, and molarity means moles divided by liters. We have a volume in milliliters, so we can just divide this by the volume of 0.0173 liters. And when you plug this in, I get 1.64 molar. Now, I did keep a bunch of excess significant figures around till the very end. This allows your answer to be the most accurate. There is some wiggle room on an in-class final. I will see how well you met that line. So, what questions do you have about this calculation? If you have none, why don't you drop a number or an emoji or the word none in the chat box so I know that you understand. Thanks for commenting, Jive Turkey. Jersey also has no questions. Ooh, Brielle asks, when it asks for concentrations, is that molarity? Yes. So concentration means moles over liters. If it means anything else, I will specify that. So Michaela asks, we have 2 questions relating to the volume of the distilled water. So Kushi and Michaela, and I'm not sure I said your first name right, both are asking, what do we do with the, I'm going to see if I can do this. Well, you know, it's not perfect. And probably should have picked any color other than gray. But this 225 mils of distilled water. So it turns out that that would have given you the concentration of your acid in molar. So if we were to set that up, and we'll scroll this back down in a minute. So if we were to have set that up, let's just scroll it over. Sorry, Tech Life. We're going to just scroll it up and we'll bring it back down in just a second. So if you had divided these. So we started with the 0.01422 moles of H2C2O4. If we had turned that into concentration, we would have divided by the volume of 0.225 liters, which would have given us 0.0632 molar. So now we have the concentration in molarity. However, in order to use the molarity, what we need to do is we're going to take our 0.0632 molar, multiply by the volume of 0.225 liters. So that would get us back to the 0.01422 moles of oxalic acid, and then we would have used our balanced equation of 1 mole multiplied by 2 moles. So the 225 in this case is irrelevant, but it brings up a great point of what about if we're given a concentration and a volume and just a volume of the other. If you are given a concentration, you need to convert to moles. So your first step, if you were to make a plan, step 1, balance chemical equation. Step 2, determine the moles of your known. Step 3, convert moles of known to moles of unknown using the balanced chemical equation. Step 4, do whatever you need to get the moles of your unknown into the right units. Sometimes they ask for grams in Alex. I tend to ask for it in concentration, so you would divide by the volume. Does that give you clarity? And has this conversation percolated any new questions that anyone might have? Earlier, McMoogie asked for titration questions. Do you have any other questions about titrations that this question didn't give you insight into? And I'm not trying to put you on the spot. Just want to make sure that you are getting clarity on this type of a question. Not seeing any questions. I'm going to go ahead and start setting up the second question on the worksheet so that you guys so that we can talk about that. Hold, please. I'm going to make this a little bit easier to read with the current setup. McMoogie says they are fine, and I appreciate the feedback. Now that we have a visual text here, you know, I'm not really, there it is. So now let's look at number 2. So this asks, how many moles of Lysol are contained within a 450 ml Lysol spray can if the can is stored in my office at 22.1 degrees Celsius and the pressure is 1.891 atmospheres? So we can see something that says a volume. We're looking for moles. We have pressure and temperature. This feels like a gas laws question. So if we think about that, we know there are 4 variables, PV and RT. So we have a volume. So that is 450 milliliters, which is 0.450 liters. Should be another 0 in there. The pressure is 1.891 atmospheres. And N is what we're looking for. So in this case, the temperature is our last one. So we have 22.1 degrees Celsius. And we're going to add 273.15. And when you do that, you get 295.25. So in this case, you can trim your temperature back one significant figure to 295.3. Either one would be fine. It should give you the same answer. So we need to solve for N. So PV equals nRT to solve for the N value here. So N equals PV over RT. So in this case, we can just start plugging in the values that you can see right here. There we go. And we can plug them into this equation. So we have a pressure of 1.891 atmospheres, a volume of 0.4500 liters. Then we have the R value of 0.08206 liters, atmospheres, mole, Kelvin, multiplied by the final temperature, which is 295.3. So I went ahead and used the sig figs here to trim that back. And so from here, once you plug this into your calculator, you should get, I don't have enough sig figs in my answer, 1.891. Oops. I get 0.03512 moles of Lysol. So if you got this answer, can you drop an emoji in the chat or a symbol? You can drop a thumbs up. You could just drop the letter. Any letter. Any comment in the chat. If you have questions, why don't you drop those in the chat box too? And we will think about how to, well, we will wait, and then we'll move on to question 3. We have an elbow cough, which I assume means we're good to go. I appreciate that. I have multiple elbow coughs happening. One of my favorite emojis, the I'm losing my marbles emoji. Sweet. A puppy. So Jersey put in a dog. I had thought my dog would pop in today, but she's taking a nap. Ooh, Clarissa asked a great question. Their question is on Alex for Kelvin. It only wants us to use 273. I would prefer that you use 273.15. I will accept both. Our final's not tomorrow. On Tuesday, I will accept either one. That works for me. To be honest, I was unaware that they only use 273. So works for me either way. Great questions. Looks like that's our only question. If you think of a burning question about this later, you can drop it in the chat and we can pull this right back up. I am going to make that question fit into the text a little bit easier. So that you guys can all see it. In case you did not print out the worksheet. So this next question deals with everyone's favorite topic, limiting reactants. So in this case, it tells us if 15.289 grams of aluminum hydroxide reacts with 17.293 grams of sulfuric acid in water to create aqueous aluminum sulfate in liquid water. How many grams of aluminum sulfate would be created in this reaction? How many grams of the excess reagent remain? If they only collected 12.403 grams, in this case, that would be of aluminum sulfate. It should say that in the question, but it totally doesn't. What is the percent yield? This equation, or this problem, has many steps. So first, let's think about what our first step might be. The first step is to create a balanced chemical equation. Balanced chemical equations are not troubling, but they require a little bit of work. So in this case, we know that aluminum hydroxide is Al plus OH. Now, in this case, it's asking you to remember that aluminum has a charge of +3 and OH has a charge of -1. So you need to have a balanced arrangement of, oops, let me move that down just a hair. Yep. Al, OH, 3. That is in the wrong place. And this is aqueous. We're going to make that solid. Plus H2SO4. And that's going to react to give you aluminum sulfate, which is Al2SO4, 3 plus H2O. Perfect. So from here, we need to create a balanced chemical equation. So there are lots of different ways you can think about doing this. I'm going to start with the sulfates. So there are 3 sulfates on the right, and so I'm going to put a 3 here. There are 2 aluminums on the product side, so I'm going to put a 2 here. When we do that, we can see that there are, and I'll just highlight these in green, we have 6 of this and 6 of this, which gives us the 6 waters that we would need here. So I didn't go through and balance this equation directly, but you could. So this question asks us how much would be created. Now, there are essentially 2 ways that you can figure out a limiting reactants question. You can either, 1, go ahead and determine the amount of product from both reactants. That will give you the limiting reactant. It makes the least product. But it's really hard to answer the how many grams of the excess reagent remain. I do not know how many questions will be on the final, but I can tell you that I will ask a limiting reactant question, and I will ask you to calculate the excess reagent. So let's go through the way that I think about limiting reactant questions in order to do that. So I like to convert each reactant to the other reactant. That's going to allow you to figure out what the balance is. So in this case, I'm going to take my 15.298 grams of aluminum hydroxide, and I'm going to convert that into sulfuric acid. And so there are 78.01 grams in 1 mole. For every 2 moles of aluminum hydroxide, there are 3 moles of sulfuric acid. From here, in 1 mole of sulfuric acid, there are 98.09 grams. So this number is 28.85 grams of H2SO4. Thank you. In that case, let me verify that my math works out, because it's entirely possible I didn't use the right number. 289 divided by 78.01. Let's go ahead and update these values here. And with these correct values, thank you for catching that, I get 28.837 grams of sulfuric acid. Now, in order to use all of the aluminum hydroxide, you have to have 28.837 grams of sulfuric acid. If you're trying to think about a picture here, like a word picture in your brain, it is asking, if I have 10 slices of bread, how many slices of cheese do I have to have? For a grilled cheese sandwich, 10 bread, you need 5 cheeses. That's what this relationship is telling you. That when everything would be consumed, those are the values. So there's 28.837 grams required. How many grams do you have? Well, you only have 17.293. That tells you that that's going to be the limiting reactant, but it won't tell you how much excess you have. So in that case, we're going to do a similar calculation using the sulfuric acid. So 17.293 grams of H2SO4. And we're going to divide by 98.09 grams in 1 mole. And there's 3 moles of sulfuric acid for every 2 moles of aluminum hydroxide. And the molecular weight of that is 78.01 grams in 1 mole. And so that gives you that you're required to have 9.1686 grams of aluminum hydroxide. So we know this information tells us that this is our limiting reactant. Now this question doesn't ask for that, but it might. But it asks us how many grams of the excess reagent remain. So the excess is the one with leftovers. So the excess in this case is going to be the aluminum hydroxide. And that gives me 15.289 minus 9.1686 grams. And since I made that number wrong the first time, let me double check. 15. Yep, that would have been wrong. Sorry about that. This app gets a little touchy sometimes. So I would get 6.120 grams. Don't forget, in significant figures, when you subtract 2 numbers, the least number of places after the decimal point controls the sig figs. So this answers really just one question. How many grams of the excess reagent remain? So from here, we need to be able to answer how much was produced with what is the percent yield. I'm going to slide it over and then we'll come on back. So from here, we're going to take our limiting reactant of 17.293 grams of H2SO4. And we're going to convert that to moles of 98.09 grams and 1 mole of H2SO4. The balanced chemical equation tells us for every 3 moles of H2SO4, there's only 1 mole of aluminum sulfate. And the molecular weight of aluminum sulfate is 342.17 grams in 1 mole. So when you plug this into your calculator, I get 20.107 grams of aluminum sulfate. So once you do this, now the last question asks, what is your percent yield? So percent yield is actual divided by theoretical, multiplied by 100. So the actual has to come from the problem. So that would be 12.403 divided by 20.107 grams. Multiply that by 100, and I get 61.685%. And if you would like, I can happily slide back over to the other side. Actually, not sure that that's like super legible, but it is legible-ish. So if you have any questions, you can drop that right in the chat box. If you do not, feel free to, I would say you could elbow cough again. Whichever way brings some sort of communication that you are good with these answers. If you got a different answer, what did you get? I will also accept emojis, thumbs ups, smiley faces. What'd you have for lunch? I had pizza. Thank you for the moral support. Potatoes. Give anyone who's thinking they might have a question just another second before we, well, you can drop it in the chat. Oh, Michaela brought a pony. I'm going to get us set up for our next exciting question of the day. So our next question, ooh, a vegan crunch wrap. Y'all are just like making the chat box really enjoyable. So this next question is, pure oxygen gas is a byproduct when chromium dioxide is produced. What is the pressure of O2 produced when 21.34 grams of chromium 6 oxide is mixed with excess, I think, chromium 2 oxide at 34.1 degrees Celsius, and the gas is collected in a 312 ml balloon? So in this case, you have a balanced chemical equation. Now, let's think about what this might be. We've got a volume. It's asking about pressure. We really only see pressure in chapter 10, let's be honest. So let's think about what we know and what we don't know. So P is what we're looking for. We have the volume of the balloon, which is 0.312 liters. And it gives us a lot of information. We have a balanced chemical equation. We have a mass. We are going to need to convert the mass of chromium 6 oxide into oxygen using the balanced chemical equation. But we only need moles of oxygen. So this is going to be moles of O2. And then the last thing we have is the temperature. And this is 34.1 degrees Celsius. And so I added 273.15, which gives me 307.3 degrees Celsius. So now we're going to use the mass of the chromium 6 oxide, or the CrO3, and convert that into moles of oxygen. I think this, yes, 21.34 grams of CrO3 divided by the molar mass of chromium 6 oxide, which is ironically enough 100 grams even in 1 mole. And then per the balanced chemical equation, we have 3 moles of CrO3 for every 1 mole of O2. So from here, we can then go ahead and balance our chemical equation or calculate the moles of oxygen. And so I got 0.0711 moles of O2, and this equals N. So this is this value. So we know that we're probably going to use PV equals nRT, and we're solving for the pressure. So P equals nRT over V. So from here, we can start to plug all the values in. Our N value of 0.0711 moles multiplied by R 0.08206 liters moles. Yep, atmospheres. Kelvin multiplied by 307.3 Kelvin. Go ahead and divide that by the volume of 0.312 liters. So when I plug all of this into my calculator, and it's a little chaotic on the screen, sorry about that, I get that the pressure is equal to 5.75 atmospheres. So let's see if I can't make these values. Nope, I cannot move these in this app, so we'll just leave those where they are. So what questions do you have about this version of a PV equals nRT question? Do you have any questions about it? If you are ready to go on to number 5, you can tell me what you had for breakfast today. I had bacon, eggs, and biscuits, and some fruit, and so much coffee. By the way, the gas loss constant, which you can see highlighted in green here, will be found on your equation sheet, as will this equation minus the circle. And I did post the equation sheet for last year's final. If you would like to include that. DJ said that he had air for breakfast today, or they had air for breakfast today, and I really couldn't have asked for any better response to this question. So we had a couple of energy drinks, toast, cereal. Oh, we have a serious question from Jive Turkey. Will we have to convert anything from pascals? If you do, the conversion factor would be on there. Noah had rice and a ton of meat, and Abdullah had caviar for breakfast. So we have some very exciting breakfasts around here. Any other question? It doesn't. Oh, back to the, sorry, someone asked a real question and I got consumed with food. Not shocking. If you have to convert from pascals, the conversion factor will be on there. I think it is on there, but I will definitely double check and make a confirmation of that. If you have a question about that. So far, you guys are doing great. Let's look at number 5. So it asks, what is the concentration of a solution when 35.182 grams of sucrose, then the chemical formula, is dissolved in 500 mils of water, and how many carbon atoms are in the solution? So on this example, when I wrote the key, I did actually think, like, maybe we should remind ourselves how you come up with the molecular weights. We've used a bunch already today, but the molecular weight is just the sum of the atomic weights. So for sucrose, it would be 12 times 12.01 plus 22 times 1.01 plus 11 times 16.00. In this case, you get 342.34 grams per mole. So you just sum those up. For my class, and for any values that I determine, you will use 2 decimal places with traditional rounding, 5 and up, round up, 4 and down, round down, from the values on the periodic table. I'm pretty sure Alex likes you to use every decimal place known to humanity. I don't care that much. So once we have that information, we're going to go ahead and convert to moles. So to convert to moles, we're going to take our 35.182 grams. We're going to divide by this molar mass. In 1 mole, there are 342.34 grams, and that gives me 0.10277 moles. And as we talked about earlier, concentration is moles over liter or molarity. So we're going to take this value of moles and divide that by liters. So to determine molarity, which is moles divided by liters, you're going to take your 0.10277 moles and divide it by 0.5000 liters. And that gives you 0.2055 molar. Before we go on to the second question, any questions about this calculation? About molarity, about moles over liters, about how to convert grams to moles? While you drop those in the chat, I'm going to go ahead and convert or calculate how many carbon atoms are in this solution. So the number of atoms is directly related to the number of moles. So I'm going to again use this 0.10277 moles of sucrose. Go. 0.10277 moles of C12H22O11. And then in 1 mole, there are 6.022 times 10 to the 23rd C12H22O11 molecules. And for every 1 C12H22O11, there are 12 carbons. And so once you plug this in your calculator, remembering how to put in your exponents, you're going to get 7.4. Hold on, that's not looking very neat. 7.4266 times 10 to the 23rd carbon. Get back here. So what questions do you have about using grams to determine moles, moles to determine molarity, or in order to determine the amount of atoms in a solution? And I will highlight in green what you would be given on your equation sheet from this calculation. Any questions? If you have no questions, you can tell me your favorite candy in the chat box. I have two favorite candies, Skittles and the gummy bears that come in the gold bag, the Haribo one, Haribo, whoever they are. Those in the gold bag, those are my favorite. They're really my weakness. So you can drop your favorite candy in that chat box to let me know that you are ready for the next problem in the deck. So Brielle asks, why did you use Avogadro's number for the number of atoms? That is a great question. So to convert from moles to atoms, we need to know how many atoms there are. And in terms of, in 1 mole, we know that there's 6.022 times 10 to the 23rd atoms. So you could have also set this equation up slightly differently. So I'm going to move this up in order to show you that. You could have taken your 0.10277 moles and then gone from 1 mole of C12H22O11 and multiplied that by 12 moles of carbon. Because for every mole of sucrose, it is composed of 12 moles of carbon, 22 moles of hydrogen, and 11 moles of oxygen. And we know that from the molar mass. From here, for every 1 mole of carbon, there are 6.022 times 10 to the 23rd. And it doesn't matter the order in which you do that, but that gives you information. Does that help answer your question about why we used Avogadro's numbers? It looks like in terms of candy snacks, we have some chocolate covered Oreos. Those sound delicious. I will be rating the candy bar in my home as soon as this is over. We have Kit Kats, we have Almond Joys, we have a chocolate bar. Mahi, it's hard to say if she was talking about Kit Kats or Almond Joys or the chocolate bar. They're really all chocolate. We have some Twix. We have a single non-chocolate from Shea, which is Jolly Ranchers, which are also delicious. Sweet. I'm glad I could help. I'm glad you asked, Bria. So it looks like we are all ready for number 6. I'm gonna roll up to the next one. Ooh, electron configurations. Everyone's favorite. Mahi says she likes all the chocolate bars. So it works. I'm glad. So as a reminder, the words draw mean I'm asking for you to do this. 1s, 2s. The words write mean that I want 1s2, 2s2. Make sure that you put the right one where I ask for it on the final exam. So it asks us to draw the electron configuration for rhodium. Which I did not bring a periodic. So it is in the 4D block, and so it's 1s, 2, 2s. I'm going to go ahead and draw my lines out first. So don't forget Hund's rule when we get to p orbitals or any degenerate orbital, 1 in each orbital, then go back and refill them all. Which I then promptly forgot to do for the next one. So rhodium, if you remember the slides from chapter 6, it's at the very end of the 4th video. all of the exceptions are highlighted in pink. Rhodium is an exception. So rhodium promotes one electron out of the 5s into the 4d. So it would have been this, but it promotes one of these all the way over here to give you this as the electron configuration. There are some patterns for this. You would need to be able to know. There's no easy way. You just need to memorize them. So they're highlighted in pink on that back at the very end of the 6.4 or at the end of the chapter 6 slides. So Elric asks, would noble gas notation be acceptable on the test? Only if it says you can use it. If it doesn't, then no. If it doesn't say you can, but it's going to say you can't. Because I do want to see that you know the order in which they all show up. So the next question says, for rhodium 3+, so for rhodium 3+, we're going to start with the 5s. From here, we need to remove let me make sure I got my So Jersey asks, how come there's 8 in the 4D instead of 7? Because rhodium is an exception and there's only 1 in the 5s. Which is why you promote a single 1 in extra into the d electrons. It's a good question. So let's continue to think about rhodium 3+. So we need to remove 3 electrons. The question becomes, which ones do we remove? Now, for a transition metal, the first electrons leave from the s orbital. So I'm going to highlight in red all the ones that we're going to take away. We're going to take away this one, then this, and then this. And so when we write out the the electron configuration for rhodium, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 4d6. Jersey has solved her complication. I'm not sure what element she was looking at. Maybe ruthenium, which is very close to rhodium. The periodic table on the final will be the same one that you've gotten all semester. It will have the names of the elements in there, in case you suddenly had a panic about that. So Brielle asks, which video on the playlist shows the exceptions? 6.4. It's at the very end. If you look at the chapter 6 slides, it's at the very end of the deck. And Brielle, I will just send you a screenshot of the exceptions from the slide deck so that you can have that. It's a great question. Any other questions about number 6? If you do not have any questions, you can, I feel like we've already talked about a lot of snacks. You can tell me your favorite season via emoji or in the chat box. Mine is spring because I really love flowers. I do not love the pollen that we have going on here really everywhere, but it's really making my allergies crazy. So if you have any questions, drop it in the chat box. Jive Turkey, how about this? I will, when I post a link to this, I will include that into the same announcements. Because don't take this the wrong way, Jive Turkey. I don't think your name is on the roster as that, and it will just be easier. I will just post a screenshot of that slide in the announcement that contains a link to this YouTube Live. Ooh, we have several votes for spring. Cassandra's a big fan of summer. Elric says anything that's not summer. Fair. You are right. It is summer year-round here, except for a few weeks in winter. Okay. Ooh, we have a vote for fall. A couple more springs. Ooh, Shay's a big fan of fall. I like your emoji selections. I mean, I liked all the emoji selections. Jersey's a big fan of summer. Ooh, move that all the way up. Oh well. So our next question says, a student in the research lab needs to utilize formaldehyde in their experiment. The formaldehyde we have is a liquid with a density of 0.982 grams per cubic centimeter. How many milliliters should they add to their flask if they need to use 75.281 grams? Now, density came to us in chapter 1 many, many moons ago. So let's remind ourselves what density is. So density equals mass, typically in grams, divided by volume. In things like milliliters, liters, cubic centimeters. So it can be in lots of things. I know Alex will use different things. I will tell you if I want you to solve for the density in grams per mil or grams for something else. So we have the amount of grams that they need. So we have 75.281 grams. Now, we have a density. We can use density just like a unit conversion to convert grams into cubic centimeters. So 0.982 grams and 1 cubic centimeter. Now, you may not remember that 1 cubic centimeter is the same as 1 mil. And so when you plug this into your calculator, you will get 76.7 milliliters. So density, the hardest thing is remembering that you want the units to cancel. Because what I've seen in the past is you might have taken your 0.982 grams per centimeter, cubic centimeter, and multiplied that by 75.281. 0.281 grams. And this value, which we'll just call box, would be in the units, grams squared per cubic centimeter. And that's not the right unit. So you want to make sure that you're paying attention to the units in order to get that to work. There are a variety of other ways that you could have tried to manipulate these, but this is the easiest way to do it, in my opinion. If you have questions, you can drop those in the chat box. If you do not, you can tell me. I'm trying to think of another question that you guys can drop in the chat box. What your favorite vegetable is. Now, I know vegetables, not everyone's favorite. You can write that you hate vegetables. But I really like roasted broccoli. I'm just going to put it out there. It's very good. A little lemon juice, a little bit of Parmesan cheese. It's really good. So if you have a question, you can drop that in the chat box. If you also want to tell me what your favorite vegetable is, I'll take that as well. Feel free to use emojis. Ooh, we've got a taker for broccoli and asparagus. Great choices. Ooh, I feel like broccoli is making a comeback. Michaela says, Whiteacre peas. Yes, Cassandra, we will accept mushrooms. Cassandra says mushrooms. Jersey opted for the roasted zucchini and squash. Ooh, Noah comes out with an excellent selection of roasted Brussels sprouts with Asiago sprinkled on top. Lovely. And McMoogie opted for grilled asparagus or beets. Very unique. And I've gotten distracted by our vegetable conversation. We have another vote for Brussels sprouts. Ooh, and Shay comes in with probably the most unique of the day, in my opinion, of onions, raw, sauteed, fried. I do like a good fried onion, like a good onion ring, but raw onions are not my... I'm going to have to pass on this. It's for me. Okay, so doesn't look like, let me confirm. We had no questions on this one. So on number 8, we have 50 grams of 0.2 molar sodium chloride at 24.1 degrees Celsius is added to 100 grams of 0.1 molar silver nitrate aqueous, also at 24.1 degrees Celsius, in a calorimeter. The temperature increases to 25.2 degrees Celsius as silver chloride forms. Assuming the specific heat of the solution in the products is 4.184 joules per gram Celsius, calculate the amount of heat in joules produced. Also, what is delta H reaction in kilojoules per mole of silver chloride? So, there are a variety of ways that you need to do this. I will admit that I posted this question, I was working on the key today, and I realized you probably needed this information. So 1 gram is equal to 1.00 milliliters, or the density of both of these solutions is 1.00 grams per mil. So you can usually make that assumption during the final. If you needed something, I'd be able to tell that to you. So from here, now we can think about this problem. So there are a couple of different ways, and you can think about which part needs to be done first. I always feel like the balanced chemical equation should go first. I know, suspicious. But let's write that out. So we have sodium chloride, NaCl, aqueous, plus silver nitrate. We do not need those brackets, so we'll just go ahead and take those out. Also aqueous, and that's going to give us silver chloride, solid, plus, in this case, the do-si-do reaction gives you sodium nitrate. Now, it doesn't ask you to remember whether or not it is going to be a precipitate or an aqueous solution, but all nitrates are soluble, so we know that this is aqueous. So that was just the participants. So we can look back and see that this is a balanced chemical reaction, 1-to-1 moles for everything. So from here, if we know that 1 gram, we do not need the 1 gram per mil yet. So the first thing it's asking us for is the specific heat of the solution. No, to calculate the amount of heat. Heat is Q. So Q reaction is equal to negative M C sub S delta T, the water. Now, in this case, we are able to calculate these things. So the M total is the total mass of 50.0 plus 100.0, which gives me 150.0 grams. We know that C sub S is 4.184 joules per gram Kelvin. And from here, we also have delta T, which is 25.2 minus 24.1, and that gives us 1.1. Now we can plug all of this into our calculation of negative 150 grams times 4.184 joules per gram Kelvin multiplied by 1.1, in this case Kelvin. Go ahead and make that dot a little bit bigger. When you plug this into your calculator, I get negative 690.36 joules, which goes down to negative 690 joules, sig figs. So this gives us part of the information. So this gives us the amount of heat in joules produced. And so that is this part. Nope. You know, I really shouldn't have done this. It worked so well the first time. I'm gonna stop while we're ahead. So we have that. But the second part asks us, what is the delta H reaction in kilojoules per mole of silver chloride? Now, we have to ask ourselves, is this a surprise limiting reactants question? So it's possible that it could be, but we can actually think about the grams per mole of these two values. So if we know that 1 gram, but first we have a good question from Brielle. Why did you use a negative in the equation? So in this case, Q reaction is negative M C sub S delta T, because the thing that we are measuring is actually not the reaction itself. We're measuring the change in the temperature of the water, which is what's housing the reaction. So if you think about the specific heat capacity of like iron or anything else where it's going to change temperatures, you don't need this. But because it is of a reaction, we're going to use this equation every time. Shay phrases the question slightly differently. Is there something in the question that determines the plus or the minus? It is a great rule of thumb to use, this value right here. If the specific heat capacity is 4.184 of the water, and we're measuring a reaction, then you're probably going to want to use the Q reaction is negative MC sub S delta T. If it is any other value, you want to use the other forms of the equation. So we could almost annotate our sheet to say the C sub S of water. So we have the total mass of both solutions in water plus C sub S of water multiplied by the delta T of the water. In that case, we could measure. That would be how you would use this. You can also just use Q equals MC sub S delta T. When you use that value, the downside could be that you have to figure out whether the heat is leaving the water or going into the water. And then you would have to assign the sign of your Q value in this way. Otherwise, if the specific heat capacity is 4.184, use this equation. If it's not, use the one that's a plus sign. Great questions. All right. Oh, I remember where we are. If you have another question, you can drop it in that chat box, and we'll talk about how to calculate delta H reaction. So delta H reaction is the heat divided by the moles. Because in this case, we know that it's 690 joules, but only for 50 grams of 0.2 molar sodium chloride. Like, that's not in moles, that's not in a value we could use. But we know with the density of water, then we can convert the 50 grams of the sodium chloride into, let me go ahead and move these things over here. So for our 50 grams of sodium chloride, it's 1 gram is 1 milliliter. 1 milliliter converted into mil. There are 1,000 milliliters in 1 liter. We're going to multiply that by 0.2 molar. And that is 0.01 moles of NaCl. And we're going to do the same thing for the silver nitrate. So we're going to take our 100 grams of 1 gram and 1 mil. Then we're going to convert that into 1,000 mils in 1 liter. And this is just 0.1 molar, which ironically enough also gives you 0.01 moles of silver nitrate. But we need it in moles of silver chloride. Now, if the sodium chloride and the silver nitrate are in the same ratio, that's a great news. We need to make sure that our balanced equation is 1-to-1, and it is. Sorry. So what we can now think about is just using the 1-to-1 relationship. So we know if there's 0.01 moles of moles here and 0.01 moles here, we're also going to have 0.01 moles of silver chloride. So we could set that up of 0.01 moles of NaCl. For every 1 mole of NaCl, there's 1 mole of AgCl. So in this case, we are going to then take our negative 690 joules. We're going to go ahead and convert to kilojoules. So 1,000 joules in 1 kilojoule. And then we're going to divide this whole thing by no one can see that, by decimal 0.01 moles of AgCl. And that gives me negative 69 kilojoules. All right. So Brielle asked questions. So if we're using 4.184 to determine the reaction, it's going to be negative. Yes, that is correct. I feel like this question was a little more chaotic than I meant. But what questions might you have other than the ones that we've talked about? Or if you still have questions about which equation to use, you can drop that right in the chat box. If you don't, why don't you include your absolute favorite emoji? Mine is the siren. I like to send it to people when there's something urgent or not urgent. It doesn't have to be important, but I'll send 3 in a row, which means something exciting is happening. Sure thing. Happy to move back to the slide on the right. Doesn't look like a lot of other questions are percolating to the top. I am going to go ahead and start setting up for our last question. Well, that worked better than I expected. So Jive Turkey asks, how did you get 0.2 molar? That came out of the question. So I'm going to try this, and we all know it's only going to mildly work. That's the wrong thing. So right here, it tells you that it's 0.2 molar NaCl, which is where that value came from. So the other one right below that is just 0.1. So the masses change those values. It's a great question. You are always welcome, and you should ask questions. Don't feel bad. It's a little chaotic with the screen and everything else. So Brielle would like us to go back over this one more time, and I am more than happy to do that. So let's get everything set up. Sorry, my app is a little touchy. I'm going to use the yellow highlighter to, that's not what I'm going to use. I'm going to use a red pen to basically tell each step. So for this question, it tells us about an equation. So the very first thing I did was write and balance an equation. Then it asks for us to calculate the amount of heat in joules produced. So I decided that we were going to use this equation where Q reaction equals negative m C sub S delta T. Then the third step was to figure out all of the values. You could do two independent calculations, one for the sodium chloride and one for the silver nitrate, and add those together. In this case, because they both have the same specific heat, we can use M total. So we added the masses, we wrote down our specific heat, and we subtracted the temperatures, T final minus T initial. Then we were able to solve for the Q of only the small sample, but it asks for delta H reaction in kilojoules per mole. So then, and this question is a little bit complicated because it gave us a reaction. And we needed to make sure that there wasn't a limiting reactant because it's dividing by the moles of silver chloride. So in this case, from here, I am going to slide over to the other side because I ran out of space. I calculated the moles of sodium chloride and the moles of, this would be number 4, of silver nitrate. Because the equation is a 1 to 1 to 1 to 1, and these two values are the same, there is no limiting reactant. Then I chose either one, converted that to moles of silver chloride. Then, for number 5 is I took the joules, converted those to kilojoules, and then divided by the moles, because this is kilojoules per mole of silver chloride. Don't feel bad about asking for us to go back over it. Don't forget, this will, I'm going to say immediately, it's going to be very quickly immediately, get posted onto my YouTube channel, so you could, please, I don't want to say don't, but it will be up there for you for forever, so you can go back and look at that later if you have more questions or just want to watch me walk through it one more time. Great question. Well, you can drop any other questions in the chat. Let's draw our Vesper structures. And we'll turn that back into a darker color ink. So for each of these, it asks in the question, which I did not post up here, to draw the Lewis dot structure and Vesper structures. And then we're being asked to name the electron and the molecular geometry. Don't forget, all lone pairs, all formal charges. So for A, we have PCl5. So the valence electrons in this case are 5 for phosphorus and 5 times 7 for chlorine, and that gives us a total of 40. So a Lewis dot structure is you're going to stick the central atom in the middle. Then you're going to start attaching stuff to it. Then I'm going to give everything on the exterior octet. Then you want to ask yourself, do I have any lone pairs left over? So if you count these up, all of your electrons, all 40, have already been used. So now we just need to put this into a Vesper structure. From here, phosphorus is connected to 5 things. Those 5 things give it a steric number of 5. A steric number of 5 is a trigonal bipyramidal, which looks like this. I think that's a little close. So we have 2 axial positions in the equatorial plane. We have 1 in the plane of the paper, 1 in front and 1 in back. So we're going to go ahead and add all of our elements. And in my class, regardless of what was talked about in lab, you have to show your lone pairs here. So now we have our Vesper structure, and our electron geometry and our molecular geometry are both trigonal bipyramid. So for all of these, they work pretty much just the same, and so we can look at those in this way. So I am going to scroll up just a little to give my space for the BrO2 plus. So the valence electrons here are 7 plus 2 times 6 minus 1, which gives me 18. We're going to put our 2 oxygens on there. Now we're going to see how many of these we can give octet to. McMoogie asks, will you give us the EG-MG chart on the test? No. You will need to have memorized that chart. Hopefully having a take home. So Shay Wilson asks, that chart will not be provided. You hopefully have started to memorize that chart. But I will not be providing it. It will not be on the exam. It's not in the equation sheet. So here we have 2, 4, 6, 8, 10, 12, 14, 16. This gives us 18 electrons, but this bromine doesn't have octet. So we're going to take one of these lone pairs, give it a double bond. And so now everyone has octet. So we need to ask ourselves about formal charge. So the formal charge of bromine is 7 minus half of 6 minus 2, which is positive 2. So we have 2 plus here. For this oxygen, it's a minus. And so this is exceptionally hard to see. In this question, so now we need to draw a Vesper structure. So there are 1, 2, 3 things connected to BrO to the bromine. So that means we have a steric number of 3. So we have something that looks like this. We're going to connect our oxygens onto it. And your formal charges and double bond should be shown. So the electron, so it's trigonal, planar, bent. So the next question is, are the angles necessary for full points? The angles are only necessary if it asks for it. So make sure you read the whole question and answer all of the different parts that I've asked for the structures. Great question. It doesn't ask for resonance in the problem, so you would not need to provide both structures for this. Double bonds and lone pairs are required in my class on Vesper structures. So you should have this. And this bent is slightly different than the bent that water is with a base tetrahedral. So let's look at COH2. Go ahead and roll those. Oh, I'm going to wait a second. And I will calculate, I will write out. First. Oh, Noah's question was answered before it came to me. So Brielle asked, could you have drawn this linear as well? So could you have drawn, did you draw this structure? Nope. Oh, we have a never mind when I was working that out. Even if you had drawn this other structure, they still would be bent. Great question. So let's look at COH2. So keep in mind, for the Vesper structures, there are a limited number of molecules, so you may have seen these on your mini exam 5 or in the worksheets that we've already seen. So for COH2, it's 4 plus 6 plus 2, which gives me 12. Carbon in the center, and then we're going to stick our hydrogens and our oxygen on it. So we've used 6, 7, 8, 9, 10, 11, 12. So this uses all of our valence electrons. But we have to ask ourselves, what about octet? So the carbon only has 6 electrons around it. So we are going to remove these 2 and make a double bond. Now carbon has octet. Octet for hydrogen is 2. And oxygen has octet, and none of these have formal charges. So from here, we can draw our Vesper structure. There are 3 things connected, which gives us a steric number of 3. And it looks like this. And so the electron geometry and the molecular geometry are both trigonal planar. So in this case, when we think about the D, the last one, which is the, we'll just move this, make that a little smaller. So for the last one, which is the arsenic hydroxide, this one is a little deceptive. So in this case, the OH molecules, we are going to remember that we're going to just sub those out for chlorines. I will draw the arsenic hydroxide structure for you. It just gets a little chaotic. But in this case, you would have 3 times 7 plus 5, which gives you 26. So we're going to put our arsenic in the center, connect our chlorines. So in this case, we've used 24 of our 26 electrons. We can then add the other 2, and this gives us all 26 have been used. No need for double bonds. So in this case, there are 4 things connected to our chlorine. No, the arsenic, sorry about that. So once they're all in there, we can now make a steric number of 4, which is tetrahedral. And we can put our lone pair and our chlorines on any of these axes. And they look like this. And so this would be tetrahedral, trigonal, pyramid. If you are super curious what the arsenic hydroxide would have looked like, so the arsenic hydroxide looks like this in a Lewis dot structure. And so arsenic hydroxide, if you think of the OH as a single entity, you could have left them together, which would have given you this. So when you take this connection and make it into the Vesper structure, it gets a little chaotic. So now we have an oxygen. Sorry about that. Hey, kiddo. Sorry, my pup's here. Now where was I? Oh, we have an OH there. And this structure over here, this would be a version of that structure. You could have also left them together. Either one of them is fine. It was unintentionally more difficult to draw than I had envisioned. So what questions do we have about Vesper? What questions do we have about any topic that we've talked about this semester? I'm happy to stick around for a little while and answer some questions. If you have no questions, you can drop. You can let me know what your dinner plans are. Hopefully you guys are not partaking for, air multiple times a day. But if you don't have any questions, you can tell me what you're doing for dinner in the chat box, and I will see you on Tuesday, or feel free to stop in office hours tomorrow. Don't forget about your Alex pie. Your Alex Pie is open until Tuesday. So when you sign in, if you have topics left to complete, it should be allowing you to do that. If you are not seeing that, send me an email and I'll check on that. Elle asks, yes, you can access anything right now. When you sign in, everything should be unlocked. In that case. Thank you guys for showing up today. Your Alex is definitely still open. When you sign in, you can get access to anything. My office hours tomorrow. That's a great question. I have no idea what time I'm there. They're in the announcement that came out on Friday. So Elric's asking about this. And no, they do not need to be together. It's freely rotating around the wedge bond, so they can be separate. It looks like you guys are having some excellent dinner plans tonight. I'm pretty jealous. I'm going to have, I think roasted Brussels sprouts, because I have some in the fridge. A delicious baked chicken coated in pesto with a side of roasted potatoes. It's going to be a good night here. You guys are so welcome. Please stop in office hours tomorrow if you need anything. You can send me an email and I will be glad to help. I'm going to finish this. There's some post things that need to get done. And then it will be live on my channel for watching later, as well as the other thing that you guys might need is I will post the exception sheets. I knew I was looking for something else. Y'all have a fantastic afternoon. Enjoy the sunshine. I will see you on Tuesday night, if not before.